Bon dia. Today, for me, it's an opportunity to present Francesco Nosenzo. I met him in a very casual way. He arrived to Barcelona up to 2 months ago. He came to my office and just asking, say, I'm going to stay here in Barcelona for a time. And if I can find any collaboration with you or your people or your the research groups that are here in Barcelona, I'm open to work with all of you or whoever is interested in. Francesco, as you can see, is a very, very young man. He did his PhD in Dora-Maira. He's going to talk about metamorphic petrology, evolution of ultra high pressure rocks. I guess that we are going to discover this world of decompression structures, radial fractures, coesites. I guess that a bit. Okay. Well, he did his bachelor and master's degree in the University of Torino in geosciences.
Department of Geological Sciences.
Yeah, okay. And from his thesis, PhD, he has written up to the moment 6 international papers. So I guess that here we have a small diamond, and we'll see. So we want to enjoy with your talk. Francesco, and thank you very much for coming here in Barcelona and have your time to explain us a little bit about Dora-Maira Massif. Yeah. Thank you.
Yes, thank you, Gemma, for this nice introduction. And a big thanks to, of course, Geosciences Barcelona and the University of Barcelona for organizing this talk. It's really a pleasure for me to be here and to be able to discuss with you about exciting science. And so today I will present some of the results from my PhD. And so what I've been trying to do during these years is to try and shed light over the processes happening at subduction zones. In particular, the question is what happens when the continental crust is subducted? And spoiler alert, the easy answer is that for the most part, remnants of an older orogens or the older orogen are recycled and metamorphosed for a second time. I have chosen these 2 images to illustrate the title of the talk, because I think they show well how we will jump back and forth between 2 different scales. A larger scale, the scale of tectonic and orogenic belt, and the smaller scale, the scale of the metamorphic minerals. And also they show well the 2 types of approaches that we can use to study these processes, and so a more fieldwork approach and a more lab-based approach. So we will first take some time to recall what is subduction, and in particular what is continental subduction. We will then take a look at an example of a tectonometamorphic terrain made of continental crust that was deeply subducted. And this is, as we said, that Dora-Maira Massif in the western Italian Alps. And then we will introduce 2 open questions regarding continental subduction, and we will try to give an answer. And finally, some take-home messages. And you will see this wheel at the corner, so you can follow where we are in the talk. So let's recall some basic tectonics. In this sketch, I am showing in yellow the continental crust, and in green the oceanic crust interposed between the 2 continents. So the question is, what happens when the 2 continents converge? Well, during a first stage, the oceanic crust, which is thinner and denser, is subducted below one of the 2 continents. This means that it is buried at depth, where it is mainly lost into the mantle. And an example of ongoing oceanic subduction, as you know, is the one below the Andes. Then, if convergence continues, the whole oceanic crust can be consumed until the 2 continental margins collide. And so this leads to pervasive deformation of the continental crust with overthrusting and imbrication of several continental nappes. And the intense uplift at the surface generates an orogenic belt. And of course, a spectacular example of continental collision is the one between India and Asia with the Himalayan belt. Let's now see what happens to the rocks when they are subducted. So, in fact, they will experience metamorphism in response to the changes in pressure and temperature conditions. And this metamorphic evolution can be visualized in a pressure and temperature diagram, or PT diagram, with the lithostatic pressure being converted to depth. So as the rocks are subducted, as they are buried, they will experience an increase in PT conditions, known as prograde metamorphism, and until they reach a peak conditions, which will be recorded by the formation of high pressure or even ultra high pressure minerals. And that's because, as we know, the lithostatic pressure increases with depth, and the temperature also increases with depth according to the local geothermal gradient, which at subduction zone is typically low because colder superficial material is constantly brought at depth. So at peak conditions, the rocks will reach high pressure and generally low temperature metamorphism, recorded by these minerals. But then some slices of crust can detach from the downgoing slab and be brought back towards the surface. This process is called exhumation and is, of course, accompanied by a decrease in pressure, which may in part overprint the high pressure metamorphic record. I will just flip this diagram vertically, upside down, with the pressure increasing vertically, because that's how we will see it from now on. And so the metamorphic history of the rocks is actually a precious record of the path of the crust within the interior of the Earth. And thanks to exhumation, we can now walk on the surface of the planet and sample rocks on the field that contain this mineralogical evidence of having been subducted. So the idea is to study subduction by investigating the metamorphic history of the rocks that have been subducted and exhumed. And so up until the 1980s, this was the conceptual model of evolution of convergent plate margins. And so only the thinner and denser oceanic crust was thought to subduct, whereas the thicker and lighter continental crust was thought to be too buoyant to subduct. But this started to change when we started to find high pressure or even ultra high pressure minerals in continental rocks as well. As we mentioned, we know well coesite as a famous ultra high pressure mineral. Coesite is a polymorph of quartz, stable above 27, 29 kilobar. So we are really in the high pressure part of the diagram. For reference, the tripole point of kyanite, andalusite, and sillimanite is down here. And so coesite was discovered for the first time in continental rocks in the Dora-Maira Massif in the Western Alps here. And in the same year, but a few months after, in the Caledonites in Norway. And this discovery was groundbreaking because it proved that even the continental crust can reach depth greater than 100 kilometers. And so these discoveries were made in the 80s. And since then, we have done some progresses, of course. In fact, we have, for example, detected ongoing continental subduction using seismic imaging. So today we know that continental subduction somehow really happens. but many of the processes and mechanisms connected are still unclear. And we will see some of these when we will talk about the two research questions. First, I want to introduce still another concept, which is the one of polymetamorphism. In fact, it is well known that the continental crust can undergo multiple tectonic cycles, and these are generally called Wilson cycles. And so at the end of continental collision and orogenesis, a new cycle can begin with rifting of the continental crust, oceanic spreading, and then once again convergence with subduction and a new orogenesis. So the crust that has been recycled throughout multiple orogenic cycles is called polycyclic, or polymetamorphic if we want to stress the fact that they have been metamorphosed more than once. In a PT diagram, polycyclic rocks make multiple PT loops with the last cycle overprinting the metamorphic record of previous cycles. And just to give you an idea of the timing of these processes, in Europe, the Variscan orogenesis and Alpine orogenesis are separated by about 300 million years, with Alpine orogeny reworking the Variscan. So we've seen that the Dora-Maira is a very good case study to investigate continental subduction. But let's first introduce the Western Alps. So the Alps are in general the result of the collision between two continental plates. The upper plate, generally speaking, is the Adriatic plate, here indicated with these orange and yellow colors. And the lower plate is the European plate with these bluish colors. And in green, we have the oceanic units. The Dora-Maira is this tectonic window here, made of European continental crust, and takes its name because it is bounded to the north by the river Dora and to the south by the river Maira. So the famous coesite that was discovered in the 80s occurs in the southern part of the massif, which was, of course, object of many studies after that. So the geology of the area is relatively well known. By contrast, the northern part of the massif remained essentially unexplored since the 1960s. And so that's where we went to do our studies, starting from fieldwork. And by the way, after many campaigns of fieldwork and several thin sections, we also found coesite in the northern Dora-Maira. But I know you're super interested about coesite, of course, but I will not go too much into details about it, so we can talk about it later. But I will not spend too much time because this was mainly the work of my former supervisor, Paola Manzotti. And so if you're interested, you can find all the details in this paper in contributions to mineralogy and petrology. The Dora-Maira actually has a complex internal architecture with multiple tectonic slices stacked on top of each other. The units may differ for lithologies and for peak alpine PT conditions, and are bounded by tectonic contacts, here represented in black lines. In fact, not all units are coesite bearing. In the south, the coesite bearing unit, the ultra high pressure unit, is this one called the Brosasko-Isaska unit. You can forget about the names for now. And the new one that we identified in the north is this thin one here that we call the Shasteran unit. But for this talk, we can actually focus on these unit above the coesite bearing unit, which we called Moret unit. But what I want you to notice in this slide is that for the most part, the units of the Dora-Maira are depicted with this brown color, which indicates that they mainly consist of a polycyclic basement. So again, these are rocks that have been metamorphosed already before the alpine overprint. In the northern Dora-Maira, the polycyclic basement mainly consists of garnet mica schist and a few bodies of orthogneiss. I just wanted to talk a bit about the age of the protoliths of these lithologies, simply to put them in context, because later we will see the time scales of the metamorphism later. So we can use uranium lead zircon dating to constrain the age of the protoliths. In fact, the age of deposition of the pillite, protolith of the mica schist, can be constrained by the age of the youngest ditretel zircon at about 600 million years, and the age of intrusion of the granitoid protolith of the orthogneiss. These are augengneiss, which has an age comprised between 450 and 440 million years. So we can say that the protoliths of the polycyclic basement have an age comprised between Cambrian and Ordovician. But I will not spend too much time in this, also because I'm showing here preliminary data, but we have done more geochronology and we are actually able to confirm these preliminary results. Instead, let's go back to continental subduction and let's introduce a first scientific question. In fact, let's make a more detailed and realistic section of the crust. In particular, this is a model that is used to illustrate what was going on in the crust after the Variscan orogenesis, so during the Permian. And we will come back to this. But for now, let's see that the crust can be divided into a lower portion and an upper portion. The lower crust experiences a high temperature metamorphism associated with partial melting, whereas the upper crust only records a medium to low temperature metamorphism or no metamorphism. So this leads to a first question, which is, what part of the crust is subducted and exhumed? Is it the upper or the lower part? In fact, 3 models have been proposed in the literature. According to model 1, the entire continental crust is subducted, so both upper and lower part. In model 2, the upper crust detaches from the subducting plate at early stages and is accreted to the orogenic wedge at a shallow depth, whereas it is the lower crust that is deeply subducted. And in model 3, the part of the continental crust that is most deeply subducted is the extended passive margin made of slices of upper crust. And so how can we determine if the material that was subducted and exhumed was an upper or lower crust? So we have to reconstruct the pre-subduction history of the polycyclic rocks. But we have seen that this is not so easy because the rocks are pervasively deformed during metamorphism. And so the pre-subduction characters, such as mineralogies and structures, are for the most part most likely lost and overprinted during the high pressure deformation. And a new high pressure foliation will develop. Unless we are lucky, and also we know where to look in the field, and we can find local domains that in part survived the reworking and preserved relics of the pre-subduction characters, such as mineralogy. And these are generally domains that have been somehow survived, that have been preserved from the alpine deformation, sorry, from the high pressure deformation. And that's actually what we found. In the northern Dora-Maira, we found a kilometer scale domain that was affected only marginally by the alpine high pressure deformation. In this low strain undeformed domain, we can find orthogneiss at the core and the mica schist directly in contact with it. In this undeformed domain, a pre-alpine high temperature, relatively high temperature foliation is preserved, whereas the mica schist in the outside the undeformed domain display a fully recrystallized alpine high pressure foliation. But let's now see the petrology. So the orthogneiss in the undeformed domain have a foliation which is defined by biotite and white mica. Biotite is dark, black in hand sample and dark red in thin section. So this must be a titanium-rich biotite, typically stable at relatively high temperatures. And the mica is a silica-poor muscovite, so it's the low-pressure mica. And so this foliation has nothing to do with the alpine high-pressure foliation. This must be a pre-alpine foliation, relatively high temperature. What about the mica schist in the undeformed domain? So they have these centimeter-sized porphyroblast of garnet and this dark prism, centimeter long. So I am actually curious to know what you would say about these minerals. What does it look like in your opinion? These sticks. I think you may agree with me that this looks a lot like a prism of staurolite. But when you look at it under the microscope, it is completely made of an aggregate of chloritoid and phengite, so the silica-rich muscovite. So this must be an original pre-alpine staurolite that was completely replaced by an aggregate of alpine high-pressure minerals. And I want to stress how kind of exceptional this is, because it's quite surprising to find relics, pre-alpine relics, so well preserved despite the intense alpine reworking in the Dora-Maira. This is for sure a unique case in the Dora-Maira, if not in the Alps. And so, in fact, in the mica schist outside the undeformed domain, the pseudomorph after staurolite are not seen anymore. And the foliation is an alpine high-pressure foliation dominated, marked by the preferential orientation of chloritoid and silica-rich muscovite. By contrast, in the undeformed domain, the mica schist have a foliation that is defined by silica-poor muscovite. And so this must be a pre-alpine foliation, which, by the way, is parallel with the pre-alpine foliation in the orthogneiss. And what about the overprint, the alpine overprint in the undeformed domain? Well, it is completely post-kinematic. And so we can see, for example, the alpine chloritoid overgrowing the pre-alpine foliation at high angle. Let's focus on garnet, on the mica schist. Garnet is polycyclic, which means that it comprises a first generation pre-alpine in age and a second generation alpine in age. And we can see this well in this microprobe map, which shows the concentration of calcium in garnet using different colors. So the warm colors are the indicate high calcium content, and vice versa for the cold colors. And so we can see that pre-alpine garnet forms the larger portion of the crystal, whereas alpine garnet only forms thin and discontinuous overgrowth at the edge of the crystal, rich in calcium. Pre-alpine garnet displays the typical continuous prograde zoning with an increase from core to rim in iron and magnesium and a decrease in manganese and calcium. And so we can use this pre-alpine garnet zoning to reconstruct the pre-alpine PT evolution. And how can we do that? Well, we can use thermodynamic modeling to calculate isochemical phase diagrams, also called pseudosections. So I will just take some time. I don't know if there are students in the audience who would like to be recalled how we use this method. So we can use a software, for example, the React Domino, which allows to calculate phase stability starting from 2 input files. The first input is the thermodynamic database, which contains the thermodynamic parameters of the phases available in the literature. And the second input is the bulk rock composition of the studied rocks, in our case, the mica schist. And as an output, the program generates an isochemical phase diagram. So how to read these diagrams? These diagrams show the stability fields of the different minerals in a PT range for a specific rock composition. So each one of these lines represents the boundary of the stability field of a mineral. For example, in this field, the stable assemblage consists of garnet, biotite, chlorite, plagioclase with excess quartz, muscovite, ilmenite, and water. If we follow this PT path, the rock is predicted to lose chlorite and stabilize storolite. We can also calculate isoplates, which are lines of constant mineral composition in the PT space. And so, for example, along this PT path, the expected calcium content in garnet is shown to decrease. And so at the end of the day, we can constrain the PT evolution by comparing the calculated phase diagram with the observed mineral assemblages in our rocks and the measured mineral compositions in our rock. And so we did this for pre-alpine garnet. And the diagram indicate that pre-alpine garnet grew from the prograde to the peak evolution from 520 degrees and 5 kilobar as constrained by the core, up to 650 degrees and 7 kilobar as constrained by the rim. So this evolution is consistent with the Barrovian metamorphism up to the amphibolite phases. And the rock never reached the partial melting field. What about the timing of this pre-alpine metamorphism? Well, we can use monazite because we are lucky enough to find monazite included at the rim of the pre-alpine garnet. And monazite gives an age at 324 million years, which is interpreted to date the peak pre-alpine metamorphism concomitant with the growth of pre-alpine garnet rim. Okay, so we managed to reconstruct the pre-subduction history. And we can say that this Carboniferous Barrovian event is most likely associated with the Variscan orogeny, which you know much better than me. And so we can really see here how the alpine orogeny reworked part of the Variscan. So let's bring back this section of the continental crust, showing the tectonic setting after the Variscan orogenesis during the Permian. In this period, the crust was being extended and the Variscan orogeny was collapsing with an intense magmatic underplating. The lower crust was undergoing very high temperature metamorphism associated with partial melting, which may have in part overprinted the earlier Variscan Carboniferous record. And this Permian event is recorded in some basement units of the Alps, but is not recorded in the Dora-Maira, which instead preserves the Variscan evolution and never reached the very high temperature condition of the lower crust and PD conditions. So it never melted, for example. And so we conclude that in the northern Dora-Maira, the material that was recycled and subducted was a pre-alpine upper crust, not a lower crust. In terms of the three possible models of continental subduction, we can for sure exclude model 2 because the upper crust is subducted. And we tend to exclude model 1 because in the Dora-Maira we don't see the lower crust. So the preferred interpretation for the study area is model 3, which is consistent with the Dora-Maira being part of the hyperextended and thinned massive passive margin during the Mesozoic. And this is actually interesting because some authors recently proposed that the units of the Dora-Maira originally derive from different tectonic blocks bounded by normal faults scattered along the European extended passive margin. And then these units were reworked during subduction and may have reached different depths. For example, in this model of evolution of the southern Dora-Maira from Bonnet et al., they draw the units of the Dora-Maira in a very distal position along the very thin margin. And this dot here is the ultra-high pressure unit, which here is drawn as an extensional allocton. And thanks to its very distal position, it may have reached a greater depth during subduction. So this is just to show you what are the latest things that the community is talking about regarding the Dora-Maira and continental subduction. And we can also ask ourselves, why would these tectonic blocks scattered on the passive margin be made of upper crust? Well, it may be due to an asymmetrical rifting, which basically removed the lower crust from one of the margins. And so we should be able to find it in the opposite margin, in the case of the Alps, in the Adriatic plate. And so in the case of the Western Alps is actually what we see with the Ivrea zone and the Césier dent Blanche. Okay, now that we have reconstructed the pre-subduction history, we can ask ourselves a second research question. So it is well known that during oceanic subduction, the oceanic crust and the mantle release large amounts of fluids. And these fluids are then responsible for the widespread magmatism in the upper plate, as in the case of the Andes. However, not much is known about fluid circulation at continental subduction zones. And so we have seen that pylites are a main constituent of the continental crust, and the fluids are known to play a key role during their metamorphism. In fact, in general, during subduction and prograde metamorphism, the water that is chemically bounded within the hydrous minerals is liberated. And this is due to the occurrence of reactions, such as this one, where the hydrous mineral chloride reacts with quartz to give garnet and a free fluid phase, which goes out. Conversely, for the metapelite to re-equilibrate during the compression and cooling, water must be added to the system from an external source. And this fluid infiltration may be localized, for example, along late-stage shear zones and veins, and is responsible for the common pseudomorphic replacement of garnet by chlorite with this kind of mesh texture. However, let's now complicate a bit more, and let's consider a polycyclic crust that experienced a first high temperature cycle before being subducted and recycled. So at the onset of subduction, this crust will have an initial amount of water that is a function of the metamorphic evolution during the first cycle. And this initial water content represents a budget of water that can be used to promote metamorphic re-equilibration during subduction at high pressure. However, if the crust is initially dry because of the first cycle, it may fail to develop the high pressure minerals, and so fail to record the subduction history, unless it is rehydrated at some point during the history. And there may be two end-member scenarios when the timing of the fluid infiltration may occur. Model 1 says that the fluid infiltrates the rock at the end of the first cycle during a low pressure and low temperature retrogression. Whereas Model 2 says that the fluids can be introduced in the rock at high pressure during subduction. And a well-known example of fluid infiltration during subduction at high pressure has been documented in the Caledonites, in the Western Ice region in Norway. Here, the material that was subducted and recycled was a granulite facies lower crust. And because it was initially dry, it remained essentially unreactive during subduction, and so basically remained a granulite, metastable, except along high pressure shear zones where fluids infiltrated the rock and allowed the re-equilibration, and so the transformation of the granulite into an eclogite. And by the way, this fluid infiltration during subduction has been associated with earthquakes at depth. And so this is a good reason to study these processes, and a good reason why we can try to discriminate between Model 1 and Model 2, because Model 2 can be seismogenic. So the second question can be divided into two. First, is the water budget of the recycled crust enough to allow re-equilibration during subduction? And if this water budget was not enough, and so the rocks must have been rehydrated, what is the timing of the fluid infiltration, Model 1 or Model 2? So to study this, to constrain this, we can go back to our polycyclic garnet, but this time we can focus on the alpine overgrowth. In fact, alpine garnet, here is a blow up here. Alpine garnet shows also a continuous prograde zoning with a calcium-rich inner portion and a calcium-poor outer portion. So we can use this garnet zoning to reconstruct the alpine PT evolution and also the fluid conditions during the alpine overprint. But how can we do that? How can we constrain the fluids during the alpine metamorphism? We can calculate diagrams with variable temperature and water content at fixed high pressure conditions. This diagram will have a water saturation line that divides the diagram in a water undersaturated field to the left and a water saturated field to the right. in the undersaturated field, anhydrous dry minerals are preferentially stabilized because there is not enough water to fully form the hydrated phases. Whereas in the saturated field, there is enough water to not only form the hydrated minerals, but also to form a free fluid phase, which will occupy the pores between the minerals. So in this diagram, we can see that the observed high pressure assemblage that we observe in our mica schist, which consists of garnet, chloritoid, glaucophyne, fengite, silica-rich muscovite, and rutile, is stable for the most part in the saturated field. And instead, very quickly, when we go in the undersaturated field, we stabilized anhydrous minerals, such as kyanite. The rock is expected to stabilize kyanite, but we have not seen kyanite in the studied mica schist. And so this is an indication that the alpine overprint occurred at fluid saturation. In fact, if we calculate a mesochemical phase diagram using excess water, we are able to model the alpine pit evolution. And so alpine garnet grew continuously during the prograde, the last part of the prograde to peak evolution, up to 550 degrees and 21 kilobar. So, by the way, we are well below the coesite stability field. We're not a lot below, but we are below. And so we are dealing here with the high pressure unit, but not a ultra high pressure unit. So the question now is how much water was needed to reach saturation during the alpine overprint. So how much water was there in the rock before the alpine overprint? Is that enough to allow re-equilibration, to allow saturation during the alpine? So we calculate this value, which is the water content at peak pre-alpine stage, so at amphibolite phases, using thermodynamic modeling. And we can see that this value, that plots like a vertical line, falls in the undersaturated field. And about 1% more water is needed to reach saturation. So this indicates that the rocks must have been rehydrated at some point after the peak pre-alpine stage, the peak variscan. And so now the question is, when did this fluid infiltration occur? So let's go back to the field. In fact, in the undeformed domain, thanks to the absence of the alpine deformation, of the very limited alpine deformation, are preserved these ductile shear zones that cross-cut the pre-alpine foliation. In fact, the pre-alpine foliation is banded, so they must post-date the peak variscan stage. But they also must predate the alpine high pressure overprint. And that's because the high pressure minerals in the shear zones are completely post-kinematic, as in the rest of the rocks. And so, in fact, if the opposite was true, if the shear zones were active during the high pressure or after the high pressure event, we would expect the high pressure minerals to be reoriented according to the shear sense. But this is not what we see. So these shear zones must predate the alpine overprint. Let's see in detail the garnet textures in samples collected close to the shear zones and in the samples collected far from the shear zones. So in the different samples, garnet shows the same polycyclic history, which is the one that we have reconstructed so far, but the textures are slightly different. In any case, in the different samples, pre-alpine garnet porphyroblasts are intensely fractured and pervasively dissolved along the rim and along the fractures. So only relics, dissolved fragments of pre-alpine garnet remain. And then alpine garnet overgrows these fragments and seals basically the space along the fractures, overgrowing the relicts. And so what do we make of these textures? Well, they may indicate that pre-alpine garnet was intensely dissolved and most likely replaced by chlorite during an episode of low pressure and low temperature retrogression. And then after that, alpine garnet may have overgrown the relic fragments of pre-alpine garnet at the expenses of the chlorite, possibly after a long temporal gap. And this episode of chlorite formation and pre-alpine garnet dissolution may have been likely associated with a fluid infiltration. And very important to note is that the pre-alpine garnet seems to be more intensely dissolved in samples collected close to the shear zones than in the samples collected far from the shear zones. Also look at the scale is different. So this may indicate that there may be a genetic link between the fluids responsible for garnet dissolution and these shear zones. In fact, these pre-alpine shear zones may have acted as fluid pathways. Another constraint on the timing of the fluid infiltration, another clue, is given by zircon geochronology. So metamorphic zircon from the studied microschist form overgrowths around detrital cores or form entirely new crystals. And they give ages at 304 million years. Metamorphic zircon show very low thorium-uranium ratio and a non-flat heavier earth element pattern, so an increase in higher concentration of the heavier here. And this may indicate that zircon grew during garnet dissolution, and that's because garnet is one of the main sink of heavy rare earth element, which get liberated when garnet is lost, and so may be taken up by the forming zircon. And so, summarizing all of these, we have the garnet textures, the zircon at 304 million years, and the late Variscan shear zones possibly associated with fluid infiltration. So all of these point towards a fluid infiltration at the end of the Variscan cycle during a low pressure and low temperature episode, so long before the involvement into the alpine. And so model 1 is preferred for the study of rocks. And so finally, we can use thermodynamic modeling to calculate the water budget evolution throughout the polycyclic history, with first a dehydration during the prograde Variscan associated with pre-alpine garnet growth, and then a rehydration at the end of the Variscan associated with pre-alpine garnet dissolution and replacement by chlorite. And then once again, during the alpine, a slight dehydration associated with alpine garnet overgrowth at the expenses of the chlorite, and then eventually a localized hydration at the end of the alpine. Okay, so last slide, the final take-home messages. I think we have understood that at continental subduction zones, remnants of an older orogen can be recycled. And reconstructing this pre-subduction history of the polycyclic rock can give us precious insights into the subduction processes. Then for these two next conclusions, I just want to point out that they are valid for the case of the Dora-Maira. So I don't want to generalize because every case study can be different. As we have seen that some cases, such as the Caledonites, can be different. But in the case of the Dora-Maira, we can see that we can say that the material that was subducted and recycled was most likely this extended passive margin made of tectonic slices of upper crust. And the water budget of this upper crust was enough to allow re-equilibration during subduction without the need of a massive external fluid infiltration during subduction. But this was only thanks to the fact that this pre-alpine upper crust had the chance to rehydrate at the end of the Variscan cycle. And so we exclude a massive fluid infiltration during subduction, and instead the rocks likely dehydrated slightly with a moderate release of fluids. Okay, so if you are interested in the details of these topics, you can check these two papers published in the Journal of Metamorphic Geology and in Litos. But of course, you are more than welcome to send me an email at this address. Let me just thank you all the people that collaborated to these works, in particular my former supervisor, Paola Manzotti, but many others. And of course, gracias a Geosciences Barcelona and the University of Barcelona. And if you have questions, I'm happy to take them.
Questions?
Yeah, thank you, Francesco. Very interesting. We have been working in the betics we are not, I am a structural geologist, I am not a petrologist of metamorphic material, but I have been working in the betics too, in the internal units. So one question I would like to ask you, because you have been in the field, is a structural question. How thick are these units you have been where you have been collecting the samples in the field, the slices, the upper crustal slices, continental ones that you see in the field? Are they very thick in kilometers?
They are not so thick, no. In fact, the smallest one that we recognize based on petrology and lithologies is just a few tens of meters thick. And then the majority are a few hundreds meters, 200-300, and maybe the thickest one in the southern is like 600 meters thick.
Yeah, which is very interesting, because then it comes to the second or to the second question, which is when you look at the cross sections, the regional cross sections across the across the Alps or even across the betics, in general they put the internal units, the metamorphic units, high pressure and low temperature, very thick, kilometers thick. You have been showing several cross sections where the different, let's say, alloctonous units are really 7, 9, 10 kilometers thick, which is curious, because in the field you don't see the thicknesses. Can you have a question for that? An answer, sorry.
Yeah, this is an interesting question, and for sure there must be some kind of tectonic process that segregates these small and thin units, either the deformation or maybe the fact that they were originally already quite thin, because maybe they were along this passive margin, very small alloctonous blocks. But of course, then they took all the metamorphism and the deformation. So this is for sure an interesting question, and it takes, let's say, quite a lot of detailed petrology and fieldwork to identify these thin units. So if at the beginning in the 60s, when they were let's say mapping the whole Dora-Maira, they couldn't identify the different tectonic slices. Only with really fine detailed fieldwork, we can maybe identify, oh, okay, this lithology has nothing to do with the one below. And then maybe we look at the petrology, and in the garnet, a few microns thick, we find coesite, and we don't find it in the garnet below. So there must be some kind of tectonic jump in PT conditions.
So what you see in the field are very thin tectonic slices that are just one on top of the other.
Yes.
With sometimes with not too much coherence in between them.
Yes. In the case of the Dora-Maira, the tectonic boundaries are difficult to find because we are in low mountains. So it's not easy to see the mylonites. But for example, in one case in the southern Dora-Maira, which is actually what I studied for my master thesis, we have been studying a contact between two units that is relatively thick, is maybe 100 meters, 200 meters. But interestingly, is made of dismembered slices of continental and even oceanic pieces, slices. So in that case, you can map better this contact. Otherwise, they've done the map mostly with petrology traditionally, rather than structural geology.
Thank you.
Thank you. Another question here.
Thank you for the extremely clear presentation. Thank you, really. My question is, it make sense. Let me see. The question is, your conclusion is that these slices, they don't come from the upper crust that is connected to the rest of the continent or in the subduction. And I guess this implies indirectly that the amount of subduction necessary to bring these slices down to the deepest, to the peak of metamorphism is not as much as you could expect if you think this is attached to the continent.
Yeah.
So does this reduce the amount of subduction that we thought there was in the Alps?
In a way, yes.
Do you have a quantification of that? How much continental subduction? How many kilometers?
I don't have a quantification because it's not easy to reconstruct exactly the margin, how it was made. So when does the proximal part start of the continental crust and where does the distal part start? So I don't know exactly to quantify this. I mean, if we just take the pressure, could be up to 100 kilometers. But then again, you say maybe this was only the thin margin that went so deep. And that's totally possible in this case of the Dora-Maira. In fact, in a way, this solves a bit the problem of the positive buoyancy of the lightness of the crust. Because then in this case, what is subducted is not the thick, light continental crust, but is somehow a transition to the ocean. So already a thin margin, maybe with some exhumed mantle.
Higher density.
Higher density, exactly.
And that's my second question. What is the density of these slices that move up? I mean, or in different words, the mechanism that brings this up to the surface is density difference with the rest of the surrounding.
This is not so clear. I would say yes, because some studies, also for example in the eclogitic microschist of the Cesia zone, say that even at eclogite facies, this crust has a density of 2.7, 2.8. And also the thermodynamic modeling that I did shows that doesn't go beyond 3, the density of the crust. So it's still quite light. And in fact, probably the most part of the numerical models that calculate how these slices are exhumed take the density, the low density of the crust as the main driver for the exhumation. So for sure, buoyancy is the main driver.
More questions? In English. when you speak about this model 3, this upper crust that you prepare for these future slices in the Dora-Maira, you speak about these hyperextended continental margins, and in other places, like for instance in the Pyrenees, we have seen also the mantle that is exhumed. Mm-hmm. So in this area where you have been working, there are some evidences of peridotite or whatever related with the mantle.
Yeah, in the Dora-Maira, specifically, there is this unit in the south that I've been studying from my master thesis, and which is, again, let's say, shear zones with tectonic slices of continental oceanic unit and even some serpentinite. So this is taken as a possible evidence for an exhumed mantle, interestingly, in between different units. So as if in the margin there were tectonic blocks, continental crust separated by exhumed mantle. This could be one possibility.
Thank you very much, Francesco. It has been a very nice and complex history, polycyclic history. Thank you very much.
Thank you. Thank you. Gracias.